welcome to the 12th live session of Principles of Digital Engineering. So today we will be discussing on the different types of charts, and we will be finding out the upper control limit, lower control limit, and we will be drawing the charts related to that, and we will be finding out the probability of the various scenarios related to the question. So we will quickly start with the session. Let's start. The samples and observation values are given. There are 5 observations and 5 samples. So we can assume that the process mean is 21 and sample standard deviation is 1, and we have to find the per control limit for x bar chart using 3 sigma control limit. So like we discussed in this 3 sigma control, when we have the mean control chart, or sigma, for which we already discussed the formulas. So for this mean control chart sigma, the step 1 is, here we have to find out the mean, which is sum of observations by number of observations. Now here the mean is given as 21. Given. Next is the sample standard deviation is given. We have to find out the standard deviation. Step 2, standard deviation sigma x bar is equal to sigma by root over of n. This is 1 by root over of 5. N is the sample size. Sigma is given, which is the sample standard deviation. This becomes 0.447. Now for this entire table we will draw it. We will find the mean. Since in this question it is already given, but still we will find out the mean. This is the sample size. This is the observations. 1, 2, 3, 4, 5. Now 20, 90. 20, 19, 25, 20, 19, 22, 18, 18, 21, 24, 21, 22, 20, 22, 23, 23, 20, 17, 21, 22, 22, 20, 22, 21, 20. Now the mean for each observation and sample sizes. For this, sample 1 is 21.6, sample 2 is 19.8, sample 3 is 20.4 plus 21.6. Now the step 3 is finding the upper control limit. Now here z is equal to 3 according to 3 sigma mean method. N is equal to 5, sigma is equal to 1. Okay, so now z is equal to 3 according to the 3 sigma mean method. Now we know the formulas for the upper control limit and lower control limit. So here in question, the upper control limit is asked, that is x sigma x bar plus z into sigma x bar, which will be here 21 plus 3 into 0.447, which will be 22.341. Similarly, you can also find out the lower control limit, which will be x capital X bar minus z into sigma x bar. This will be 21 minus 3 into 0.447. So here the upper control limit is being asked. So it is, the answer is 22.341. So here main we have to find out. Remember that in 3 sigma control limit, the z is equal to 3, and here the sigma x bar, sigma is equal to 1, and n is equal to 5, and x bar is equal to 21. So these are the data given in the question, and we have to find out according to that. Okay, so the next question. The total number of defects in a lot is 100 and the total observations are 1000. Then the percentage of a fraction of defect is okay. So here it is asked about the percentage of the fraction of a defect. Here the number of defects are, number of defects is equal to 100. Total observations is equal to 1000. Now percentage of fraction of defects is equal to, or we can say this as P is equal to number of defects by number of observations is equal to 100 by 1000 into 100 is equal to 10%. Now this is a here we have been asked about the fraction of defects. This can also be somewhat related to the P chart, where we need to find out the fraction of non-conformities or no fraction of defects. Okay, so now moving to the next question. Identify the methods of work measurement. Which of these are the work measurement methods? So last time we discussed clearly on the different methods of work measurement, which is method study and time study. So I will show you that slide again so that there won't be any more further confusion. Now, okay, so work study, as we discussed, we'll again go through this concept as it is important. It consists of method study and work measurement. Now, work measurement, this consists of work sampling and standard data method and time study. The purpose here is to setting standard time and identification of the ineffective time. While method study here, this focuses on the jobs for improving the method of doing a job. Now, purpose, this purpose is to, it focuses, method study focuses on the method, improving the method of doing the job. But work measurement, its purpose is to setting standard time and identification of the ineffective time. So here the correct option is all of this: time study, work sampling and standard data method. Now the next question, the purpose of productivity in an organization is which of the following? So what is productivity? Productivity is so we should be able to measure the performance of an organization or industry as a function of time. Like we can say that for a particular plant, what was the productivity last year, 2 years, and with compared to that, we need to compare it to the current productivity of a particular organization. So this is the first thing we should be able to do. Okay. Now, next is, it has three purposes in total. So next, secondly, we should be able to compare the different departments, industries, sections with respect to productivity. Like there is a department A with department B. So we should be able to compare that which department is more productive, which section is giving more profits. And one more thing, if some corrective measures are being taken, so if there has been an improvement in productivity or a target has been achieved, or up to what level the productivity has been achieved, that should be also measured. So and it means that we compare the productivity of an organization with the means of comparing the actual productivity. That is, we compare the actual productivity of an organization with the planned productivity. So the actual versus planned. So the first thing is able to measure the performance of an organization or industry as a function of time. Secondly, comparing the actual productivity Actual versus planned productivity of an organization. And the third is uh, we measure the performance of the organization or the industry as a function of time. What has been the trend of variation in the productivity, how good a particular department is doing, or what was the actual productivity as compared to the planned productivity, so that we can go through the so that we can easily get through the productivity measurement. Now the third one is third one is measuring the performance sorry how good a particular department is doing, or so that we can easily get through the productivity measurement. So this was about the productivity. So according to this, the all three are the purpose of the productivity. Now the next question is, a company produces type A products. The total number of defectives is 200 and observation was taken for 20 samples. And each sample has sample size of 100. So we need to find out the 3 sigma upper control limit with the help of P chart. Now the company has type A products, total number of defects is total defectives is equal to 200. Total number of observation that is 20 samples into 100 is equal to 2000 observations. Now we have the 3 sigma chart. So first we will find out the number of defects, that is P bar is equal to, so this is somewhat like first here in your second question you had to find out the percentage of fraction of defects. Now you were again finding out your fraction of defects. So P bar fraction of defects, P bar total defectives by total number of observations. This is 200 divided by 2000 is equal to 0.1. Now, upper control limit for a P bar chart is equal to P bar plus Z. Here Z is 3 for your 3 sigma control chart, root over of P bar 1 minus P bar divided by N. Now P bar is equal to 0.1 plus 3. This is 3 sigma control. Z is equal to 3 plus 3 root over of 0.1, 1 minus 0.1 by 100. Your N is equal to 100. This becomes 0.190. Correct answer is option A. Now, the next question. The benefits offered by control chart include which of the following? Now, control charts, as we know, we have to use when there is a variation. Now, control, as we know that we have control charts for variations, control charts for attributes. So, in a total, it is asked, what are the benefits of a control charts? Well, the control charts we get to know for attributes, we get to know the control charts for quality characteristics, and by when there is a based on the nature of the characteristics, like this variable or attribute. First of all, quality characteristics. So the process capability, we already discussed that so here first of all the correct option is all of this. Now the process capability we will discuss further in the coming questions. Now the question is, when to take corrective action, type of remedial action necessary, and process capability, these all are included in the control chart. Now control charts we have for variable, for attributes. For variables we have this measurable, which can be measured. Attribute system, non-measurable characteristics like quality, uh, which we cannot quantify. Okay, so by the variables we can know the number of non-conformities or the fraction of non-conformities or the number of defects in a lot, sample, or a product. That depends on, there are variations. Now based on the variables, that was based on the attributes. Now based on the variables, now based on the attributes, we have like control charts like which it is product is good or not, we should accept or reject, it is yes or no. These are some of the variables. So so when we know if the percentage of a defects in a lot is larger, so to avoid further loss or to take action at the correct right time, we this control charts give us an idea when to take the correct initiative or when to rectify the defects and renew the lot so that there is no further wastage. So in short, the control charts, in this way we have the advantages of control charts. Now So here we have all of these as the correct option. Next question. Fraction of defective items are identified in case of which of the following? Now, the correct answer is P chart. The P chart shows the percentage or proportion or fraction of non-conforming items in a total lot. Suppose in a total like lot or total number of observations from the samples selected. Like suppose we have 2000 items from different samples, and out of this we have 200 number of non-conforming items. So the fraction will be here, this will be 10%, that is the p value will be 10%. The p value is 10%, that is 0.1. So this will be indicating that the 10% is the fraction of the conforming items. So this is the thing which we have already solved in this previous question. Here also we found the p bar first, that is a fraction of the non-conforming items. Here also we solved the fraction of percentage of fraction of defects. So basically here in this thing we will be given the total number of defects and the total sample size. From there we can find the percentage or fraction of the non-conforming items. So this is very important to find out, like when the correct action can be taken, when the remedial steps can be taken, what is the total process to be followed in case of the number of defects are high. Now the next question. The process is considered to be produce a product capable when the variations are within the control limit, variations are outside of the control limit, variations are behind the control limit, variations are behind the upper control limit. If you remember, we had drawn a chart last week, okay, where we had this quality characteristics, and this is a mean line, and there was upper control limit, lower control limit. When their variations were between the mean and above the upper control limit, that was abnormal variation due to assignable sources. When okay, this was the upper control limit, this was the mean, this was the lower control limit. This is a very important chart. Each time we discuss this. This is the sample number. Let's consider 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now this is the quality characteristic. Suppose let's assume these are the variations. Now when we have the variations beyond upper control limit, here we have this abnormal variation due to assignable sources. When we have the variations here, we have this abnormal variation due to chance. When we have the variations between lower control limit and the observations, this is abnormal variation due to assignable sources again. So what we know from here is we have the p-value, that is the fraction of the defects. Lower control limit, upper control limit. Okay, these are the given. We know p-value, lower control limit, upper control limit. Now when we see that the p bar is higher, this means fraction of the defects, fraction of the defective items increases. Okay, this means that quality is degrading. Quality of the things or products or service is deteriorating. Okay, sorry for the disturbance. So okay, this means that the now what happens is, now here this needs for the management. When the quality of the things or products or services is deteriorating, this means that the management now needs intervention in form of better expertise or better machinery or better procedures. So in this previous question, when we came across the benefits offered by control charts include when to take corrective action. This is one of the things, that when the percentage of defects are high, the management here needs to interfere. When do we need to take the correct action, when to make the correct for the prevention of these increasing number of defects. Okay, so this means now that some major intervention is required. So when it happens that the average p bar value is high, and when it is reduced also, this is when it is reduced. When it is reduced, indicating that the fraction of the defective item is decreasing. So when the p bar value is reduced, this means fraction of defective item is decreasing. Now that is one inference, and all this indicates the process capability. Now central line value, that is the p bar, indicates the process capability, or p bar value indicates the process capability or how capable a process is. Now Lower value of P bar, it will indicate that the better capability. Now when the P bar value is low, this means better process capability, showing lesser fraction, showing lesser fraction of the non-conforming items, or this will also indicate that the process can be used to produce large number of goods without producing many non-conforming items. So this is one interference. Now the center line value indicates the kind of fraction. This center line value indicates the kind of fraction which will be their average fraction of the non-conforming items and the process capability. And if the P bar value is high, this means intervention of the management. Okay, so this was about a product, how the process is capable and how to the process is considered to produce a product capable when. So the correct option according to all this is the variations are within the control limit. Now I'll also write about the center line value indicates which indicates the kind of fraction excuse me, of the non-conforming items and the process capability. Now the next question. The dimensions of manufactured product X is 5, 4, 3, 4, 4. Then what are the mean and the range values? Now here mean is very straightforward. Mean is the sum of observations by the number of observations. This is 5 plus 3 plus 4 plus 4 plus 4 divided by total number of observations is 5. This will be 4. Now range values is the highest range minus the lowest range. This will be 5 minus 3 is will be 2. So the correct option is 4 and 2. Previous question, the correct option was variations are within control limit. Now the next question. Center line is the control chart suggests. Center line in the control chart suggests desirable target value. We just discussed that when this is the center line value indicates the kind of the fraction of the non-conforming items and the process capability. Center line indicates process capability. Center line, upper control limit, lower control limit. So variation should always remain within this range. As we learned from this question, variations are within, for a product to be capable, should remain in this range for a product to be capable. Now we will important some very three important questions. Let's start. So here, okay, there is a space within this. So this here it is given of a tough bind strength of a synthetic material which is used to make carpets is known to have a mean of 50 kg, and the standard deviation is 10 kg. Sample size is 40 kg if randomly selected. So what is the probability that the sample mean will be less than 52.5 kg? Okay, so first, now for this question, using the central limit theorem, the sa the sampling distribution of the sample mean will be approximately normal. With a mean which is given, mu, we will take it as mu x bar is equal to 50 kg, and the standard deviation for that sample we can have to find out. So sigma x bar is equal to 10, which is the sample standard deviation, by root over of sample size which is 40. This will become 1.581 kg. So for this, the variation, the chart we will draw. Now this is the x bar, sigma x is equal to sigma by root over of n. This is the mean. So we here want to find that p x bar less than 52.5. As it is given, what is the probability that the sample mean will be less than the 52 points? So first we have to find the standardized value. Now this will be Z1 is equal to x bar minus mu x bar by sigma x bar. This is given 52.5 by which we found out the standard deviation mu x bar sigma x bar. This will come 1.58. Now, so we have, for these questions we have a chart where we have to find out the range where the 1.58 it will come. So for that range you will get to know this. You already can get this from slides. Refer slides. So here for this range, when we have z less than 1.58, the probability comes around 9.429 using the data given. So you have to just find out the Z. See, in 3 control sigma chart, it was always given, we assume Z is equal to 3. But here we do not know what is the Z value. So we have to find the standard value. For that, this is the process followed. After we get the standard value, you can refer to their data given and find out the probability. Okay, this was one kind of a question. So now we will move on to the next question. So the next question is, so here we have been given a lathe machine where the thickness of a part is subsequently used in assembly. So the process mean is known to be 30 mm with a standard deviation of 1.5 mm, and mu is 30 mm, sigma is 1.5 mm. Now we have to construct a control chart for the average thickness using 3 sigma limits if samples of size 5 are sample size, or n, is equal to 5. Take table below shows the average thickness of 15 samples. These are the thickness of 15 samples selected from the process. Now we have to make this on a control chart. Now we will start here. So we assume that the center line, okay. First we will draw and write simultaneously. This is the sample, okay. We will draw a bigger graph for this. Consider this is the chart, okay. So here the average thickness, you see, it comes in the range of 25 to 33, and the sample size is 15. So we will draw the chart. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This is the sample. Now the average thickness is 25 to 33. 25, 26, 27, 28, 29, 30, 31, 32, 33. So what we have to do is, first we will find out, we know the mean center line is the mean. Center line mean is equal to 30 mm. Standard deviation of the sample mean x bar, sigma x is equal to sigma by root over of n is equal to, now sigma here it is given 1.5, that is the standard sample deviation, which is here we will find out the sample standard deviation, by root over of 5 is equal to 0.671. Now we will assume a normal distribution of the sample mean thickness UCL is equal to, which we already did, that's x bar plus z into sigma x bar is equal to 30 plus 3 into 0.671. This will be 32.031. Upper lower control limit is 30 minus 3 into 0.671 is equal to 27.987. So here we assume z is equal to 3. Okay. Next, so we will first draw the center line. The center line this is the center line. Now this is the center line is equal to 30. Upper control limit is 32.013. So we will draw a line here. This will be the upper control limit 32.013. The lower control limit is 27.987. So we will draw a line this is the lower control limit 27.987. Now we have all this data 31.56 approximately it will be here. Next we will draw till 29.5 and with respect to the sample, like this is 1, here this is 2, next 30.5 is approximately here. Then we will join all this. Now 4, sample 4 is 30.72. It will be approximately here. Next is sample 5 is 28.92. Next is sample 6 is 31.45. Sample 7 is 29.7. Sample 8 is 31.48. Sample 9 is 29.52. Sample 10 is 28.3. Sample 11 is 30.2. Sample 12 is 29.1. Then 13 is 30.85. 31.55, 14, and 15 is 29.43. So this is the control chart for average thickness. Control chart for average thickness. So this is the way in which we can draw the control chart. So the last question. Data for the number of dissatisfied customers in a department stores for 25 samples of size 300 are shown in below. Now we have to construct the NP chart for the number of dissatisfied customers. So for here, first we will find out the control chart for the center line for the control chart. So center line for the NP chart. So previous we drawed a control chart. Last question, in this question we drew a control chart based for the average thickness. So this followed, here we assumed it followed a normal distribution. Now we will draw a NP chart. For this, first we have to find out the center line for the NP chart. This is, we have the total number of customers 184 by the sample size, this is 20 by is equal to 9.2. Now the control limits we have to find out. The control limits are found using the following equation. Here we found out the P bar also we can see. Now the control limit for this is found out by, we already discussed the question for this. That is upper control limit is equal to P bar plus Z whole into P bar one minus P bar by N. This is the P bar. This will be 9.2 plus 3. Z is again assumed as 3. Assume plus 9.2 1 minus 9.2. Okay, I made a mistake, sorry. 1 minus P bar by N. Okay, no, it's okay, correct. Z P bar 1 minus P bar by N. So this will be 9.2 1 minus 9.2 by 300. Now this will be approximately 18.159. Now this is for the NP chart. Now lower control limit, NP chart, same formula. So I'll just write down 9.2 minus 3, 9.2, 1 minus 9.2 by 300. This will be 0.241. Now we will plot this NP chart same way the way we did the plotting in previous chart. We know the upper control limit, we know the lower control limit, we know the center line. Now in this question we have to also find out the number of constructing NP chart for the number of dissatisfied customers. So first we will quickly draw a NP chart. So we will draw the sample and this is the number of dissatisfied customers 0, 5, 10, 15, 20. Now the sample will be till up to here as given 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 and 20. So first we will draw the center line, which is 9.2. Center line 9.2. Now upper control limit, as we found out, it is 18.159. Where control limit is 0.241. This will be somewhat very close to your x-axis. Where control limit 0.241. Now like we did, we will quickly draw the for the sample 1 it is 10. For the next sample it is 12, 8. Sample 1 it is 10. Next is 12. Next is 8. Next is we have 9, 6, 11. Nine. We have 6. Again we have now 11. Then we have 13, 10, 8, 13, 10, 8, then we have 9, 6, 19, 9, 6, 19, 'Then we have 10, 7, 8, 10, 7, 8. Then we have 4, 11, 10, 4, 11, 10. Then we have 6 and 7, 6 and 7. So from this chart we see here that sample 12 plots above the control limit, upper control limit. It indicates out of control state. So this is a special case which should be investigated. Cases should be investigated and remedial actions needs to be taken. So this was one of the point where we learned about the process control. What are the actions to be taken? That was one of the points. Remedial action needs to be taken. So now limits are revised by deleting sample 12. The revised center line and control limits are control NP is equal to 184 minus 19 by 19. This will be 8.684. Earlier sample size was 20. Now we have removed one which is out of control, and now the sample size becomes 19. The upper control limit for the NP is equal to 8.684 plus 3 whole into the 8.684. Why? Because we had the 9.2 is the center line. Now we have this new value, plus 3 into 8.684, 1 minus 8.684 by 300. This becomes 17.396. Now lower control limit is equal to 8.684 minus 3 whole into 8.684, 1 minus 8.684 by 300 is equal to 0.028. This tends to 0, minus 0.028, this tends to 0. So these are the new limits which should be used for future observations. So in this way we take the remedial actions. So as I said earlier, the benefits, this is the benefits offered by the control chart, where when to take corrective action, type of remedial action necessary, process capability. In this is the further questions. Type of when to take corrective action, type of remedial action necessary, and the process capability. These all things we come to know from this control charts. Okay, so we reach to the end of questions. Any further doubts we can discuss? We will be having one more summary session, which I will be recording and uploading, where I will be just going through a gist of all the topics we discussed, just a revision of all the topics we discussed, and you can refer to it as a short recap. All the best for your upcoming exams. Thank you so much for attending these lectures. I really hope that the numericals we discussed extensively will be very much helpful to you. All the best for your exams. Any doubts, please reach out to us. You can always post in the announcement tabs, uh, so that we will be discussing further. I'll always be there to answering these questions. Okay. Any further doubts we can still discuss. If there are no further doubts, we can end the session. Okay. Thank you for attending the sessions. Thank you all.